Good morning, everybody. Hope you're all healthy and safe. Let us continue with our chapter 6 on self-adjoint operators. So, today in this lecture, we shall be discussing about the corollary of the Hilbert-Schmidt theorem that we have discussed in the previous lectures. So, this is corollary 6.2.6, and it consists of actually 3 points. So we'll be dealing with it one by one. First, let's just go through the theorem, the corollary. That is, let H be an infinite dimensional Hilbert space, and the following are true. Okay. So the first one is, if a positive eigenvalue exists, then the maximum of norm x equal to 1 inner product T of xx is equal to that positive eigenvalue, that is lambda 1 plus. We know how we have denoted lambda 1, lambda 2 and all, right, the inequality. So keep in mind, we always assume that lambda 1 plus is greater than equal to lambda 2 plus is greater than equal to and so on, and lambda 1 minus is less than equal to lambda 2 minus is less than equal to and so on, where lambda 1 plus or lambda I plus are the positive eigenvalues and lambda I minus are the negative eigenvalues. So the first thing that the corollary states, that is, if a positive eigenvalue exists, then the maximum value of inner product T of xx, where norm x equal to 1 is always lambda 1 plus, and the minimum value of the T of xx, where norm x equal to 1 is always lambda 1 minus. Okay. The second thing about this corollary is that the inner product T of xx is greater than equal to 0 if and only if, okay, there exists no negative eigenvalues. Okay, that is the second part of the corollary, that is, the inner product is always positive if and only if there exists no negative eigenvalues. Now we know we have expressed inner product T of xx as the sum of eigenvalues, sum of positive eigenvalues and negative eigenvalues along with the modulus inner product x ei whole square, right? We had expressed it that in that manner in the previous remark. So with the help of that expression, we'll be proving the corollary. Now there is one more thing in this corollary, that is, we are going to consider instead of lambda 1 plus, I'm just going to simply consider lambda 1 plus equal to lambda plus and lambda 1 minus equal to lambda minus. Okay, so set lambda plus is equal to lambda 1 plus if a positive eigenvalue exists and lambda plus is 0 otherwise. If a positive eigenvalue exists, then set that particular positive eigenvalue to be lambda 1 plus to be lambda plus. If it is a single value, then that is the greatest one, so lambda 1 plus is equal to lambda plus. If there are more than many eigenvalues, then you have to set the largest of them to be lambda plus. If you have 3 positive eigenvalues, then choose the largest one and set that largest one as lambda plus. Okay. Similarly, case of lambda minus, then what happens is the same thing, that is, instead of maximum, here we have supremum value. Supremum of norm x equal to 1 will be norm x equal to 1 into inner product txx will be equal to lambda plus, and the infimum will be equal to lambda minus, and with the help of this inequality we'll get lambda minus into norm x square is less than equal to inner product txx is less than equal to lambda plus into norm x square. This is easily obtained if the supremum value and infimum value, because if you just see this expression, supremum at norm x equal to 1, inner product txx is equal to lambda plus. So clearly this lambda plus will be greater than equal to inner product txx, right? And into that we are just multiplying another positive value, so clearly this will be true. Or here you can treat norm x as 1, so this is just 1 itself. Okay, so similarly we'll get this inequality. So second, this inequality can be easily proved once we prove this. Okay, so let us move on to the proof of this corollary step by step, one by one. Let us just see how we can prove this corollary. So first thing that we have to prove is that the maximum and minimum is attained at the particular eigenvalues, right? So I'm going to prove the first part. So suppose that positive eigenvalue exists. Suppose that a positive positive eigenvalue exists, we know that the inner product dxx can be expressed as summation lambda I plus into mod inner product x ei whole square plus lambda I minus into mod inner product. This is how we had expressed in txx, inner product txx, right, as a sum of positive and negative eigenvalues. Now sum t of xx, inner product t of xx is equal to this. Now can I write that inner product t of xx, okay, this will be less than or equal to summation lambda I plus into inner product x ei plus whole square. How is that possible? Because all these terms will be negative, right? Lambda i's are negative in this case, so if I take the sum of these terms also, I'll get a negative value. So actually inner product t of xx is nothing but a particular term minus something. So this term, so t of xx can be definitely, or it can be easily stated that this t of xx is always less than or equal to this positive term, okay, because the second term in this expression is always going to be negative. Now each of lambda 1, lambda 2, etc. will be less than or equal to lambda each of lambda i's where I not equal to 1 will be less than equal to lambda 1 plus, right? So I can take that thing common out, lambda 1 plus into summation inner product x ei plus whole square. Now what is the reason for this? Since lambda 1 plus is greater than equal to lambda 2 plus, because lambda 1 plus is the maximum value, right? So I can say that each term will be less than equal to lambda 1 plus. So I get this. Now I'm going to write this is less than or equal to lambda 1 plus into norm x square. How is this possible? This is possible by our own Bessel's inequality, okay. Bessel's inequality states that this summation is less than equal to norm x square. Now what was our assumption? We are considering the case when norm x, we need the value of the maximum value of inner product txx when norm x equal to 1. So if norm x equal to 1, what will be, let me just write down, I have obtained inner product txx is less than or equal to lambda 1 plus into norm x square. So this implies maximum of norm x equal to 1 inner product txx will be less than equal to lambda 1 plus, right, or it is equal. So this is not less than equal, it is equal. The inner product txx is less than or equal to lambda 1 plus into norm x square. So if I suppose that norm x is 1, I get the inner product txx is less than equal to lambda 1 plus. So the maximum value of this inner product txx at norm x equal to 1 will be equal to lambda 1 plus, okay. And similarly we can prove, similarly we will get inner product if we consider the case of negative eigenvalues, inner product txx is always greater than or equal to the negative terms, right? Because if you're considering only the negative terms, then the actual expression of inner product t of xx consists of some positive terms also. So this will be greater than equal to lambda I minus into inner product x ei minus square. So and since each of the term will be greater than or equal to lambda 1 minus same expression and same concept, except we will be using the other inequality. What is inequality? Lambda 1 minus is less than or equal to lambda 2 minus, and etc. And again by Bessel's inequality I will get this is greater than equal to lambda 1 minus into norm x square. So the maximum when norm x equal to 1, the not maximum, minimum, the minimum value of inner product Txx will be equal to lambda 1. Okay, so this is how we have proved the first part of the corollary. Now we shall go on to the second one. What is the second thing that we have to prove? Second thing we have to prove is inner product Txx is greater than or equal to 0 for every x in H, if and only if there exists no negative eigenvalues, right? So this is what we have to prove. Okay, so we have, again I'm writing this expression, so we are using this expression often, so keep it in mind. Summation lambda I plus mod inner product x ei plus whole square plus summation lambda I minus into modulus inner product x ei minus whole square. Okay, so I'm gonna write this down. Now let me suppose that inner product Txx is greater than or equal to 0. Okay, so if this expression is greater than 0, then by 1, what can I say? The first part that we have proved just now, we can say that minimum of norm x equal to 1 inner product Txx. Okay, by 1, what was it? Minimum of norm x equal to 1 inner product Txx was equal to lambda 1 minus. But since Txx is always greater than or equal to 0, this is not possible, right? Because lambda 1 minus means it is a negative value. So by 1 we can say that there exists no negative eigenvalue. Okay, so that is done. Now let us see the converse part. Suppose there exists no negative eigenvalue. I don't think we have to just we have to write down all these things, because it's simple. If there exists no negative eigenvalue, then this whole term will be 0 and this term is always positive. So this is clearly T of xx is greater than or equal to 0. So the converse part is very simple. Now let's move on to the third part of the corollary. It is also very much simple. Now that is, we have to prove that if positive eigenvalue exists, okay, if positive eigenvalue exists, then we will set lambda plus is equal to lambda 1 plus. So then what we get is supremum norm x equal to 1 inner product Txx will be equal to lambda plus. So this is clearly obtained from the part 1. It is clear from part 1 of this corollary, because maximum value is inner product Txx. Maximum value is lambda 1 plus, and we are assuming that lambda 1 plus is lambda plus. So that is clear. Supremum of norm x equal to 1 inner product Txx is equal to lambda plus. Now suppose if no such eigenvalue exists, if no such positive eigenvalue exists, okay, what happens is, let's just see, eigenvalue exists, then we will put lambda plus is equal to 0, right? Now what happens if such an eigenvalue does not exist? In our expression, there is no positive eigenvalue, means our inner product Txx will be equal to summation lambda I minus into modulus of inner product x ei whole square, right? Only the negative terms will be there. And clearly the sum of all negative terms will again be negative. This will be less than or equal to 0, even though this is square and positive, but this lambda I minus will always be negative. Now what I'm going to do is, I'm going to choose xn to be en minus. Okay, let us suppose xn is en minus, then what will be txn xn? This will be nothing but summation lambda I minus, instead of x it will be xn into ei minus whole square. And what was xn? Xn was nothing but inner product en minus into ei minus. Now we know ei forms an orthonormal basis, so this value will be equal to 1 when I is equal to n, and all other terms, all other values of I, it will become 0. So this is nothing but lambda n minus into 1, that is lambda n minus. Now we know all the set of eigenvalues, it will tend to 0. We have seen in the proposition as n tends to infinity, so I get inner product t of xn tends to 0 as n tends to infinity. That is this, if you consider this as sequence, the inner product t of xx as corresponding sequence, then I get that inner product xn tends to 0. Also, what is happening? The inner product t of xx, each and every term of that sequence is less than 0. Okay, it is each and every term is less than 0 and it is tending to 0. So I can say that the maximum value of the sequence or supremum of inner product txx will be equal to 0, which is equal to lambda plus. I hope it's clear. All the terms of the sequence is negative and it is tending to 0. So the maximum value of that particular sequence will be 0. In a similar manner, we can consider that the infimum value will be equal to, okay, let me just write it down. Similarly, we get infimum norm x equal to 1 inner product txx is equal to lambda minus. So in the last part of this corollary, we had to consider two cases. One was lambda minus exist or lambda plus exist, and the other when they do not exist, that is equal to 0. So in any case, what happens is the supremum and infimum is equal to lambda plus and lambda minus respectively. Okay, so I hope the concept or the proof of this corollary is clear for you guys. So just go through the corollary once again, and we'll be using this inequality so often. So here we have the last part of the corollary. I have just mentioned in the beginning itself. It is simple from the inequality or the expression that we have obtained just now. That is, if supremum of txx is equal to lambda plus and infimum of txx is lambda minus, then this inequality is clearly obtained. So that's it for today's session. Thank you.